In this video, we are going to use the ideal gas law and the combined gas law to solve problems. Let's start with question 12. A weather balloon used by meteorologists is made of a flexible bag that allows the gas inside to freely expand. If a weather balloon containing 25 meter cube of helium gas is released from sea level, what is the volume of the gas when the balloon reaches a height of 2100 meter, where the pressure is 8.2 times 10 to the power 4 Pascal? Assume the temperature remains unchanged. So let's first write down what is given to us. We have the weather balloon of helium gas, which has a volume of 25 meter cube. Meter cube is the unit of volume. So even though the word volume is not mentioned in the question, when you look at the unit meter cube, you should know that it is volume. So I will write the volume V1 as 25.0 meter cube, and it is released at sea level. Now the pressure at sea level is 1 atmosphere. So I can write this as my pressure 1, which is 1 atmosphere. And 1 atmosphere is equal to a pressure of 1.013 times 10 to the power 5 Pascal. Then we need to find what is the volume of the gas when it reaches a height of 2100 meter. So your height h is 2100. Where the pressure, so we will write this pressure as P2, is 8.2 times 10 to the power 4 Pascal. Temperature remains unchanged, so your temperature T1 and T2 are equal. We need to find what is the volume V2 for the gas. I'm going to use the combined gas law to solve this problem. The combined gas law says P1 V1 over T1 is equal to P2 V2 over T2. And when the temperature remains the same, this combined gas law can be transformed into Boyle's law, which says that P1 V1 is equal to P2 V2. We can just cancel off these temperatures because they are equal to each other. And that transforms your combined gas equation to Boyle's law. I want to find what is V2. So you can either substitute all the values over here and shift solve, because we have the values for pressure P1, volume V1, and pressure P2. Or you can rearrange the terms and solve for V2. If I want to find volume 2, I need to divide by pressure 2 on both sides. So we get V2 equals P1 V1 over V2. Now substitute. Pressure 1 is 1.013 times 10 to the power 5. Volume 1 is 25 meter cube. Divide by pressure 2, which is 8.2 times 10 to the power 4 pascals. And when you solve this, you get volume of the gas at a height of 2100 meter to be equal to 30.88 meter cube, which you can round off to 31 meter cube. Question 13. Starting at 0 degrees Celsius, how will the density of water change as it is heated from 4 degree to 8 degrees Celsius? So my starting point is from 0. Then from 0 degree, you go to 4 degrees Celsius. And you need to find how will the density of water change when you go from 4 degree to 8 degrees Celsius. Now, density of water is maximum at 4 degrees Celsius. So at 4 degrees Celsius, the density of water rho is maximum. So when you go from 0 degrees Celsius to 4, the density in this situation will increase. Once it increases, it becomes maximum at 4. And then when you increase the temperature beyond 4 degrees Celsius until 8, the density now will decrease. Because this density is maximum at 4 degrees Celsius, so at any temperature above 4 degrees Celsius, the density has to decrease. So your answer will be, as the water is heated from 0 degrees Celsius, the density will increase until it reaches a maximum at 4. And then when you increase the temperature further, the density of water will decrease. Question 14. In a certain internal combustion engine, 0.0021 meter cube of air at atmospheric pressure and 303 Kelvin is rapidly compressed to a pressure of 2.01 times 10 to the power 6 Pascal and a volume of 0.0003 meter cube. What is the final temperature of the compressed gas? So let us first write down what is given to us. I have a 0.0021 meter cube of air. Meter cube is the unit of volume. So I will write this as volume of air, which is V1, 0.0021 meter cube. And this air is at atmospheric pressure. So my pressure P1 is equal to 1 atmosphere, which is equivalent to 1.013 times 10 to the power 5 Pascal. And 303 Kelvin. Now Kelvin is a unit of temperature. So I write my temperature T1 as 303 Kelvin. Then it is rapidly compressed to a pressure of 2.01. So this is my pressure 2.01 times 10 to the power 6 Pascal. And the new volume is V2, which is 0.0003 meter cube. You need to find the final temperature, which is T2. So again, we are going to use the combined gas law, which says P1 V1 over T1 equals P2 V2 over T2. I want to find T2 over here. So you can just use shift solve because I have all the values given to me in the question and I need to just substitute all the values, shift solve to get T2. So you could just write all your values as P1 is 1.013 times 10 to the power 5. V1 is 0.0021 over T1, which is 303, equals P2 is 2.01 times 10 to the power 6. V2 is 0.0003 divided by T2. And you can use shift solve over here to find the value of T2 as 858.8 Kelvin. Now you can either do this or we can rearrange the term to solve. So how do we rearrange this term? I want to find what is T2. So I cross multiply. I move T2 to the top here, bring P1, V1 at the bottom, and move T1 on the other side. So I rewrite this expression. T2 equals P2 V2 multiplied with T1 over P1 V1. Then you can substitute and get your answer. P2 is 2.01 times 10 to the power 6. V2 is 0.0003. Temperature T1 is 303 Kelvin. Divide by pressure 1. Again, the same thing I'm substituting here, but this time we just rearrange the terms to solve it. And when you solve this, again, you get T2 as 858.8 Kelvin. If they ask you to find the final answer in one significant digit, or if they ask you to round this to the nearest 100, you can round off your temperature T2 to 900 Kelvin, which I can also write as 9 times 10 to the power 2 Kelvin. And this is if they ask you to find your final answer in one significant digit. Question 15. What is the volume of 1 mole of a gas at atmospheric pressure and a temperature of 273 Kelvin. So we have the mole of the gas, which is N, 1 mole, and the temperature T is 273 Kelvin. Pressure P is 1 atmosphere, which is 1.013 times 10 to the power 5 Pascal. I need to find the volume V. To solve this, we will use the ideal gas law equation, which says PV equals nRT. I want to find the volume, so I will divide with the pressure P. V equals nRT over P. Again, if you do not want to rearrange the term, you can substitute all the values here and shift solve. So now substitute. Number of mole is 1. R is the ideal gas constant, and the value of R is 8.31 Pascal meter cube per mole Kelvin. So substitute for R, 8.31. Temperature is 273 Kelvin over the atmospheric pressure, which is 1.013 times 10 to the power 5. Now, when you solve this, you get the volume of the gas to be equal to 0.02239 meter cube, which you can round off to 0.0224 meter cube. Question 16. How many moles of air are in a refrigerator with a volume of 0.635 meter cube at a temperature of 2 degrees Celsius? If the average molar mass of air is 29 gram per mole, what is the mass of the air in the refrigerator? So here the question has given me the volume of the air in the refrigerator. So I will write volume V equals 0.635 meter cube. Then we have the temperature T, which is 2 degrees Celsius. I will convert this temperature from degree Celsius to degree Kelvin. And to do this, I have to add 273 to the temperature in degree. That gives me the temperature in degree Kelvin as 275 Kelvin. The molar mass of air, which is capital M, is 29 gram per mole. In the first part of the question, we need to find how many moles. How many moles means we need to find the number N. And in the second part, we need to find what is the mass of the air. So let's start with calculating the number of moles first. To find N, I'm going to use the ideal gas law, which says PV equals nRT. And if I want to find N, I'm going to divide with R and T on both sides. So that gives me N equals PV over RT. Now, since the gas is air, the pressure of air is the atmospheric pressure, which we write as 1.013 times 10 to the power 5 Pascal. So that is the pressure I'm going to use here in my question. Sometimes the pressure is not given, but they give you the gas. So air, the pressure of air is the atmospheric pressure. So now let's substitute. I get my N equals 1.013 times 10 to the power 5. Volume of air in the refrigerator is 0.635 meter cube over R. Again, R is the ideal gas constant, which is 8.31 times the temperature, 275. And when you solve this, you get the number of moles N to be equal to 28.1 mole. So this completes the first part of the question. In the second part, they want us to find the mass of the air. Now there is a relationship between the molar mass capital M, the number of moles N, and the mass of the gas small m. And that is N equals small m over capital M. And if I want to find the mass of the gas, I just have to multiply my molar mass with the number of moles. So we will write small m, which is the mass of the gas, equals N times capital M, where N is the number of moles, capital M is the molar mass. Now let's substitute. N, which is calculated, is 28.1. Molar mass of the gas is 29 gram per mole. And when you solve this, you get the mass of the air to be equal to 0.81 kilogram. Question 17. Compared to the particles that make up carbon dioxide gas, the particles that make up helium gas are very small. What can you conclude about the number of particles in a 2-liter sample of carbon dioxide gas compared to the number of particles in a 2-liter sample of helium gas if both samples are placed at the same temperature and pressure? Now, according to ideal gas law, we know that PV is equal to nRT. So the number of moles of a gas is proportional to PV over RT. Now, if you keep the pressure and temperature same, this number of moles will be only proportional to volume. And here the volume of the two gases are the same. You have 2 liters of carbon dioxide and 2 liters of helium gas. So since the volume was same, the number of particles also has to be the same. So the number of particles in a 2-liter sample of helium gas has to be equal to the number of particles in a 2-liter sample of carbon dioxide gas, even if helium particles are much smaller compared to carbon dioxide. Because volume does not depend on their size. Volume depends on the amount of space that they take. And if they have the same pressure and they are held at the same temperature, as well as the volume is the same, the number of particles present inside the sample will also be the same. So your answer becomes there are equal number of particles in the two sample. In an ideal gas, the size of the particle is not relevant to the volume of the gas or the pressure exerted by the gas.